which is super easy. So integral of sine is what? Negative cosine. Negative pi and pi. And it turns out that cosine term just drops out. So it's just 3 times 2 pi, so what, 6 pi? So that's the mass of this thing. It's an awful lot like finding the area under a curve, and in fact the area below the density curve is the same thing as the mass. Right? And you can see why this is just 6 pi, because I can just cut off this part and put it here, right? It's a rectangle. So what's far more interesting is looking at the center of mass, which is like a balance point. So what I want is, if I'm holding up this object here, it's definitely off center, right? If I try to hold it up from a pinpoint right here, it's probably going to tip over this direction, right? So the question is, where do I need to put a pinpoint so that it would balance here? Okay, so I would say the torque on a point located at X is what? It should be like a mass times a lever arm, right? Times a gravitational constant. So it's going to be a gravitational constant times a mass times a lever arm. Okay, and so let's see what I want. This is going to be gravitational constant times rho of x dx. Now, if the center of mass here is C, if that's the center of mass, what's my lever arm look like? Should look like x minus C, right? Because it's the difference from where I am to the center of mass. Okay, so what I want is for the net torque on this thing to be 0, right? Because if I balance it on one point, I want it to not turn. So that's where I'm getting center of mass from. So this is the torque on one point. So the total torque on this object should be G times the integral of rho of x dx times x minus c over wherever this thing occupies. Well, I want this to be 0, and the question is, what does c have to be to make that happen? Okay, so first of all, do you see where the gravity doesn't really matter? Just multiply it in there. I'm going to drop that because you can divide both sides by g. 0 divided by g is just 0. So what I'm looking at is integral of rho of x times x dx minus the integral of rho of x times c dx is going to end up being 0, right? So that's the same thing as saying that the integral of x times rho of x is equal to the integral of c times rho of x, but c is a constant. I can factor it out. Okay? So this is going to tell me that the center of mass that I need is going to be the integral of x times my density function divided by just the integral of my density function. So this is how you find the center of mass. So if you, like I said, if you take Calc 3, which I know a lot of you have to do, you'll have two coordinates of the center of mass, and in one of them you'll have x times the density function, and the other one you'll have y times the density function. So the same idea is scale up to more interesting objects. All right, so let's find the center of mass of this guy. x was sine of x plus 3. Occupied the space from negative pi to pi. Okay, so we know the mass. Now we just found that. What was that?
6 pi.
It was 6 pi. Okay, we just did that. Oh, by the way, do you notice that this is just the mass on the bottom? So you integrate x times the density on top and divide by mass. Let's see. Okay. So if I want the integral of x times rho of x, from negative pi to pi, that's going to be the integral of x times sine of x plus 3x. Okay, so what kind of integral is this? It's just simple, yeah, right. So, yeah, but this one we need integration by parts. You want to do table method? Let's do that, because it's quick. So x sine of x, derivative of x is 1, derivative of 1 is 0. Integral of sine is negative cosine. Integral of negative cosine is negative sine. And I need to multiply diagonal pairs, add them up with alternating signs, right? So this should be, let's see, negative x cosine x plus sine of x. And then the integral of 3x is just going to be 3/2 x squared. Okay, so and this is negative pi to pi. All right, now in this one, now sine of x, that's just going to cancel, right? Because that's the same at pi and negative pi. What about this term? Same? Doesn't make any difference, yeah, because pi squared, negative pi squared are the same. So that doesn't contribute, that doesn't contribute. So this should be negative pi times cosine of pi, which is negative 1, minus pi times cosine of negative pi, which is negative 1. Okay, so 2 pi, is that right? It better not cancel, I don't think it's 0. Yeah, okay. So this is 2 pi. Alright, so where's my center of mass going to be? 2 pi over 6 pi, so it's at 1/3. Alright. And there's nothing particularly special about the 3. I think that's true for any amount of space below the sine curve. So that's just the amount that the sine throws it off. All right, so mass and mass density are not terribly difficult. You can see where a lot of times in these you run into integration by parts just because you're multiplying something by x. All right, the other thing that you can run into that's like this is probability calculations. If you ever take a stats class, you may run into this, or if you take the upper division probability in the math department. Okay, so the idea behind this is you've got what's called a probability density function. You know, so it might be, you know, something that looks like this. Now definitely we're going to need rho of x to be bigger than 0. Can you think of any other restrictions that we might need in a probability system? What do you figure the total mass of the system ought to be? Ought to be 1, right? Because the way you do it is, if you've got a density function, if I integrate from here to here, the area under that curve should give me the probability that whatever I'm calculating lands between these two numbers. So you have a random variable x, the probability that x lands between a and b is calculated as the integral from a to b of your probability density function. Okay, so the integral from negative infinity to infinity of your density function better be 1. Now you can have them with finite domains and you're really just integrating from 0 to 3 or something like that. But you can't have these with infinite domains. For example, a normal distribution that you see all the time in your intro stats classes. Or Gaussian distribution. This is a super infuriating thing because the density of this guy, it's 1 over sigma square root of 2 pi e to the negative 1/2 x minus mu over sigma squared. Okay, so this is a normal distribution with mean mu and standard deviation sigma. So it is something that you run into all the time. Can anybody say a problem with calculating probability for this function?
No.
We can't integrate e to the negative x squared. We don't have an antiderivative for that, right? So here's the most common distribution that shows up in the universe. Law of large numbers and central limit theorem says an awful lot of things we study go according to the normal distribution, but the one that shows up all the time we can't actually do computation. So there's that. All right. So let me give you an example of one that does show up a reasonable amount. An exponential distribution what's it? Yeah, that's probably the way I would do this because a series for e to the negative x squared, and so you could tweak this so that it's done by a Taylor polynomial and approximate it that way. Yeah, either that or just do some numerical technique like trapezoid rule or Simpson's rule or something like that, where you're basically doing the Riemann sum calculations by hand for very large m's and very small delta x. So either one of those would be productive. All right, so exponential distribution on weight times. All right, so your density is rho of x is, let's see, actual number in it. Yeah, like 5e to the negative 5x. Okay, and that's just on x greater than 0. So what that says is, here's your density function. Looks like this. And it's saying the probability that my wait time is in between these two should be the integral from here to here of that density function. That's what it means. So you've got very small probabilities of very long wait times, right? So the probability that I wait more than 100 years would be the integral from 100 years to infinity of this, which is small, but positive. Yeah, so this comes up in estimations in insurance companies. If they want to figure out the probability that you live long enough to pay off a series of payments, they may use this distribution for it. That's not accurate because there's very little possibility that you live more than 200 years. But for approximation, it's not terrible, and it's easy to work with. What's it? Yeah. So, all right. First of all, is this a proper probability density function? Of course, yes. Otherwise, I wouldn't be doing the example. But what do I need? Rho of x is positive. It's an exponential function. And if I integrate from 0 to infinity, 5e to the negative 5x, what do I get? This is the limit as c goes to infinity of something evaluated at 0 and c. 5e to the negative 5x just integrates to e, or I guess negative e to the negative 5x. So I've got the limit as c goes to infinity of, let's see, negative e to the negative 5c plus 1. Oh, and what does this do as c goes to infinity? First term goes to 0, so the whole thing ends up going to 1. So it does actually have a total mass of 1. Now you notice that the height of the probability density function can be bigger than 1, right? So if I plug in 0 into this thing, I get 5. So that doesn't actually matter what the height of the probability density function is. It matters what the total mass is. That just means it's a whole lot more likely to be close to 0 than any place else. Okay. So, and of course, if I wanted to find out under this distribution the probability that my wait time is more than 10, well, it would just be the integral from 10 to infinity of this guy, right? So this is the limit as c goes to infinity of negative e to the negative 5x at 10 and c. So the only difference is the bottom limit, right? Top limit's still got to go to 0, and you just end up getting e to the negative 50. So now you can see where as this number gets bigger, this number is going to get smaller, right? So again, your probability of waiting gets less and less the longer the time is. The interesting thing about this is, and I'm not going to go through the the computation for it, but basically, however long I've been waiting, the probability that I wait a little bit more is always the same. So it's the reason they use this in the insurance industry. That's called constant force of mortality. It basically says no matter how old I am, the probability that I die in the next short while is always the same. It's like there's sort of a constant force that's trying to kill me, but it doesn't change. So it's one assumption that you can make. Yeah?
When you integrate the 5e to the negative 5x, where's the constant 5 go? Does that get outside the...
Remember you chain rule, right? If I differentiate e to the 5x, I'm going to have to multiply by 5. So it's accounting for that. It's not big enough to really do a u substitution on, but it's the same idea. All right, so what is called the expected wait time, or in general, the expectation of your variable. Expectation is the same calculation as center of mass. It's supposed to be a weighted average of your output values where what's used as a weight is a probability density function, right? So it's going to end up being the integral of x times your density function from 0 to infinity. So in this case, it's the integration by parts, but it's not a bad one. So this is the integral from 0 to infinity of 5x times e to the negative 5x. All right, so let's use tabular method. I've got I'm going to do it as x and 5e to the negative 5x just to keep my constants small. Derivative of x is 1, derivative of 1 is 0. Every time I integrate this function, I got to divide by negative 5, right? So I'll have negative e to the negative 5x and 1/5 e to the negative 5x. Alternating signs. This is going to be the limit as c goes to infinity of negative x e to the negative 5x minus 1/5 e to the negative 5x. Okay, so what do you figure this does? If anything good is going to come from this, top limit better be 0, right? Otherwise, we're not going to get a finite number. That does actually happen sometimes. You can have a distribution with an infinite expectation, even though it's got finite values. All right, so, and that would say on average you wait forever, which nobody wants that. So, all right, this is 0 minus, what do I get when I plug in 0? First term is 0, second term is negative 1/5. So on average, you wait 1/5 of a time unit here. So maybe say 1/5 of an hour is 12 minutes. Now do you see how that correlates directly to the thing that showed up in your density function. If you had a 7e to the negative 7x, your average weight would be 1/7. Right, so it's you'll see this sometimes in a statistics class. Exponential distribution with mean theta is your density function rho of x is 1/theta e to the negative x over 3. So 1/theta plays a role of 5 in ours. Mm-hmm.
I'd get the same result if I were to integrate from b to infinity of that of the density function, and that's equal to 0.5, right?
No, because the mean's not the same thing as the median. Median is half the probability is above it, half the probability is below it. Mean is the weighted average of the probabilities. They're usually close, depending on what the distribution is, but they're not necessarily the same. All right, I think we're out of time. We'll pick this up next time with whatever.